I'd like to talk to you about incidence, prevalence, and duration. Um, and I know this may be a little confusing to you because you're seeing the words incidence and prevalence, which are counts, and primarily we're going to focus on rates, which involves division, multiplication, and well, it involves division and multiplication, and the multiplication is by a constant. Um, I want to give you an exercise. This is a group or a unique group example, so we're using it for heuristic purposes or teaching purposes, is what the word heuristic means. And the first question I'd like you to think about and consider in looking at this graphic is, what is an incidence rate? Um, we know first that it's going to involve a count, right? We're going to have to count, and then we're going to, for the numerator, and then we're going to have a denominator, which is going to be the total population or the special population. And we know it's for a year period because it's not specified otherwise. So once you hear that word incidence, you know immediately that that's for a year period. And once the word rate is added, you're going to do some minor math to come up with the answer. So one of the things necessary about an incidence and incidence rate is that it requires a diagnosis. And without a diagnosis, we don't know what a case is. And I've made that point over and over again. And so in these kinds of situations, that's very important. Now, I want to review the formula very quickly. All of them are going to be called a ratio because you know the major category is a ratio, right? And ratio includes rate, ratio, and proportion. And so we're dealing with the number of new cases. That's why we need a diagnosis, and it's during a specified period of time, which you know is 1 year, and then the total population at risk, and it's times a constant to 10 to the nth. Now, incidence can come in different intervals. It can be a half year, it can be a quarter year, it can be 2 weeks. But if it's not specified, you always assume incidence, or excuse me, 1 year. Okay, so when we ask and look at this, I'm going to ask you, what is the incidence rate of cancer in this exercise that I just showed you? Now I want to go back to that slide, and I want you to look at it very carefully with me. Okay, so in looking at this, what are you going to count as incidence? Well, we know by looking at this that the incidence going to have to do, it's going to be during an annual period, and we have an annual period on top shown, and then we have a new case because it's newly diagnosed. So we're looking at the D's, and we're going to have 1. This one would not count. 2, 3, 4, 5, 6, 7, 8. So we have our incidence, or our count, is 8. Okay? Now, in this particular heuristic example, it's not realistic, but it's to help you learn about incidence, is that we have a total of 12 cases. So you'll always want to look at this legend to make certain that you understand what is being represented in any given table about incidence or prevalence. Now I want to go back to where we were, okay? And this is probably a good review for you too, and you can make certain that you're familiar with it. So the number of D's in this particular case was how many? We said it was 8. And the population at large was 12 patients that were at risk. So of those 12 patients, only 8 of them were diagnosed as having a new disease. Now we selected a constant, and we select constants primarily with because we want to communicate with a certain audience. We also selected this constant because the number of cases is not very large. And I'll talk more about constants and selection. You won't have to worry about that on the test. It will be specified as to which constant you're going to select from. But I want you to understand and know and be savvy about the utilization of constants. So our incidence rate is 67 cases per 100 individuals, or about 2/3 of the cases are diagnosed with cancer. Now, normally you won't see cases or individuals written after numbers, but in learning it, it's important to understand what it is that you're talking about. What you would see is 67 per 100. Now, people often ask, well, why didn't you use a 10? Why didn't you divide it by 10? You're saying it's 10 to the nth power. Well, we could have divided it by 10, but that would have given us 6.7 cases, and again, we'd rather report a integer rather than a fraction. So this is the reason we don't do that. Next, if it's not specified, if an incidence rate or incidence is not specified, assume annual. Now again, I mentioned it can be for other lengths of time. Remember, it's annual if it's not specified, and that's an important factor to take into account. So if somebody says the incidence is da 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 da, you're just going to assume that that's for a year period, which a year can be 365 days, or if it's leap year, it can be 366 days. Okay, I want to give you another problem, and this has to do with prevalence. Okay, and we're going to compute or calculate a prevalence rate. Now, I'd like you to focus on the top here because it's sometimes difficult to understand just how this operates, but you can see that at the beginning, this would be January 1, this would be February 1, March 1, April 1, and so on. Now, my question to you is, what is the prevalence rate at July 1st? Okay, so we're going to look at the prevalence on July 1. Now, one of the things that you have to take into account is you have to know the definition of what prevalence means. So right now you should be thinking about, I wonder if I really understand this. Well, okay, we know that prevalence takes into account new cases, existing cases, and recurring cases. So you don't want to be confused about that. And we said prevalence is a more comprehensive term than is incidence, right? Now, when we look at this, we're going to do we're doing a prevalence rate, so you know there's going to be math involved, but we have to do the count first for the numerator, and we'll do that together. So which cases am I going to count? Well, I'm going to count case 2, and that's because it is it happens to be a new case, but nevertheless it occurs on July 1. We're going to count this case number 3 because it is an existing case. This one is a newly diagnosed case, so we're going to count that one. This is an existing case. We're not going to count case 7 because it falls out of the time frame. We're going to count case 8. We're going to count case 9. We're not going to count case 10, and we're not going to count case 11 because it falls out of the time period of interest, and we're not going to count case 12. Now, in this example, we did not take into account recurring cases. It didn't happen. And I don't want to get into that right now because I will talk about that later as well. And our total population, our denominator, is 12. Okay, so let's go on and see what our answer is. But before I do that, I want to point out that prevalence is a slice in time. So we took a slice in time about prevalence on July 1. Now, there's some problems in doing that, and if prevalence isn't specified, it's point prevalence, right? Now, if you took prevalence at a different period, like with the flu, and it would have been in October, we would come up with quite a different answer than if we looked at prevalence rate for flu in the summer. Okay, so what is the prevalence rate for cancer on 7/1? Recall the point prevalence rate. Recall that it's a point prevalence. So we have the total individuals with diseases at a specific point in time that includes new, existing, and recurring cases, and we didn't have any recurring cases. And if we go back and count, we will have 7 cases, and out of 12 patients, which is a population at risk, and this is a study group, and we're going to use times 100. So our answer in this particular case is 58.3 cases per 100 individuals. And you said, well, now last time you told me we ought to deal with an integer, and now you have 58.3. This seems confusing to me because you've got a fraction. Well, if prevalence rate and an incidence rate, we want to use the same denominators so that they are comparable. Otherwise, I would have to multiply the other one by 1,000, and this would be, if I did that here, it would be 583 per 1,000. But we also have the burden of wanting to be able to communicate with an audience about the prevalence rate of a disease within a certain small group or population. Okay. But in this case, another way to say it is that a little more than half the cases out of every 100 people have cancer. And that's a meaningful explanation to most people. Now, okay, Prevalence, again, reflects the number of new, existing, and recurring cases in a population and is more comprehensive than incidence, and it includes incidence. So, and I'm talking about rates here, right? Prevalence includes incidence. We've talked about that. Prevalence alone is a count. We've talked about that. Prevalence rates vary by time and have a special notation depending on whether we're working with a special population, a larger geographic group, or the nation, or the world. And what I'm showing here is a national statistic where the cancer rate would be 7 per 100,000 population. So we used a special study group rather than using the national population, is why we have an answer that's different. Okay? K is a reference group that usually makes a numerator a whole integer. I showed you a case where it didn't. Government reports usually report to thousands, and sometimes this is just what occurs, and oftentimes when you want to make comparisons, you want to use the same denominator so that you can make them. Okay, so if you want to talk about the difference between incidence rates and prevalence rates, you're able to do so. Next, I'd like to talk about duration. And duration has to do with once patients have been diagnosed with a disease, how long do their signs and symptoms last? Duration answers that question. People always get confused about what duration means, so I underscore that with you. Now notice what is used in order to derive the answer of duration. So we use point prevalence rate as a numerator and incidence rate as a denominator, as the denominator, got my tongue twisted there for a minute. Be sure the constants are equal. We already talked about that in the necessity, because we're going to do some math with these. Okay, next. What factors influence duration? Well, the rarity of the disease has an impact, because you'd have a very small prevalence rate and a small incidence rate, so that would influence your answer. Rare diseases can influence the numerator and the denominator, or a low incidence and a short duration of a illness decreases prevalence. So I'm just showing you various ways that these three influence each other. That's the main point I'm trying to get across. When calculating duration, use point prevalence. You want a point prevalence rate, not the period prevalence rate, and the annual incidence rate. Now people say, well, I don't get this, because when you're talking about point prevalence, you're talking about a point in time. And when you're talking about incidence rate, you're talking about an annual period. And it doesn't seem logical to divide one by the other. Perhaps not, because of the difference in the length of the time period. Perhaps not, but this is how it's done, and it's been done this way for years, and that's how the figures are derived and reported in the Control of Communicable Diseases Manual by Heyman that I mentioned previously. Okay, so here's different ways that we can solve for different elements or different information that you might want to know. And duration is the primary one that we're going to focus on, and you'll want to learn and commit to memory and etc. This is just a manipulation of these three, and you can do that. You've learned this kind of manipulation through your earlier mathematics classes. Okay, now I want to use it in our example, our heuristic, unrealistic, if you will, example. But nevertheless, we want to get the points across to you clearly. It says the incidence rate and prevalence rates must have equal constants so they cancel. I mentioned that. I've said that about 3 times, so I'm hoping that's going to stay with you. Recall from the previous examples, we had 7 cases and 12 patients at risk, and I think our answer was 58.3. And now what we're doing is we're fractionating, we're dividing 7 by 12, and that's how we come out with a 0.5833. Now with the incidence rate, we're doing the same thing. We're dividing 8 by 12, and we're coming out with another fraction of 0.667. And now we have a peculiar figure that is 0.8749 years. And most people don't know what 0.8749 years means. I don't either until I convert it. So I'm going to take that figure, because that's duration, and I'm going to convert it to a year period. And notice what we have is we're defining year as 365 days. We're defining a month as 30 days, and ultimately we're going to divide 365 by 30 to come up with 10.6 months. Okay, so that's our answer. That's how long the disease lasts. So in some cases, an acute disease could last this long, okay? And these diseases could be contagious or not, and this is one way to categorize diseases as contagious or not contagious. It could be a chronic disease. It creates more problems, of course, and more economic burden. Chronic diseases do, and logistic issues and personal problems and family problems, etc. And this could be an acute disease again, and it could be lethal. Okay, I'm just trying to relate duration to you in some meaningful way as to what it really means, and how you might think about it. Why do we want to know duration? It helps identify an unknown disease. So if we didn't know what the disease was, we could look through the Control of Communicable Disease Manual, and we could look for diseases that had a duration, because duration is listed, or as well as incubation period, which I'll talk later. But duration would help us identify what type of disease that we are dealing with. And so that's an important element in disease identification. And once we know how long disease, what the duration is, it helps with planning, prevention, protection, and control, and perhaps quarantine or ICU restrictions and public health precautions if the disease is contagious. Okay, I'd like to talk about indices of mortality. Okay, and what we find is that the 2 most common indices of mortality are crude death rate, okay, and crude birth rate. And how come these are the most common? Because that's what everyone does. They are born and they die. And how long you live is the only varying factor in that. Now, all people pass through this process, and usually in underdeveloped countries, they're not rich in data. costs a lot of money to collect data. The U.S. is rich in data. We have databases of all kinds, and there's secondary data sets available from various government agencies, and I'll point that out and where you can get them. And one example would be from the Centers of Disease Control, and there are many other government agencies that have data that you can normally buy. They don't just provide it to you free, but these data sets are used by many different disciplines, including sociology, and oftentimes somebody that's getting their dissertation in sociology will use a secondary data set. So that's just an aside. So one of the things that I mentioned, that most countries in the world collect crude death rates. Okay, not crude birth rates. And for everything that I'm talking about here, we have a certificate of some type. You have a death certificate. You have a birth certificate. And if I'm talking about any other measures that we talked about between birth and death, there's also certificates for divorce, for separation, etc. Okay, so but again, that's the reason why. And the crude death rate makes it possible to compare death rates between countries, and that's what we're often wanting to do. Okay, let's talk about. It's a summary statistic. Okay. It looks at the death rate of a population. It's crude because it includes the entire population. We don't fractionate it in any way. We take, and you know the definition of a rate. What's considered in the numerator is taken from the denominator. So the numerator and the denominator are related, and eventually I'm going to show you other formulas to help make crude rates specific rates, and we're going to show you about 15 of those, or excuse me, about 18 of those. The nice thing about a crude rate, even though it's crude and it doesn't follow the mathematical principles that you're usually aware of things being separate and distinct, it can be calculated with the minimal information. And here we have a document in front of us that says somebody has died, and you know that you can order a death certificate from the county health department. They run anywhere from $10 to $20 a piece, and usually if someone dies, the mortuary will give you certified death rates. Make certain you get as many as you can. Now, in the denominator, we're usually looking at the mid-year population, ideally from the census or perhaps from the U.S. population clock. Now, what I'm talking about here, this is different. This is not your heuristic example I'm talking about. I moved to a population level. So these are populations of countries that we're looking at. So these are U.S. population statistics. I told you about the world population statistics, so I don't want you to confuse when I'm talking here with the heuristic example I was talking about earlier. Okay? Why do crude rates, what do they tell us? Well, we want to know whether death rates are going up or down. Now, well, I can tell you in America, the death rates are remaining fairly constant, which is not a good sign. they should be going down. We have other countries that are doing far better in death rates in terms of decline than the U.S., and I'll show you graphics of that, and you can ask yourself why. So we can look at time and trends across years. We can see progress or not. Also, we want to use them for planning purposes. If we're not making progress, how can we make strides especially with chronic diseases? We need to be doing a lot more planning and a lot more thinking, and we need to talk about protection and control strategies that are going to help the population. So all of these come from crude information. In addition, we're looking at it's an inexpensive method of surveillance, because everybody's required to have a death certificate. So it's not an extra requirement, it's not an extra financial burden, it's part of what society expects. So death records, especially in the U.S., are required by law in most countries, and we look at them for the leading causes of death, to help set priorities. Usually we don't just say a death. We don't look at just a crude death alone. There's more specific information, what are you dying from, etc. But if we're doing a cross-country comparison, they're very valuable to see how we're comparing against other nations. Now, these are standard statistical terms, and these are terms that I really expect you to know. There's a multitude of epidemiologic statistics, okay? I'm not requiring you to know all of them. And these are standard national ratios from the Bureau of Statistics used with the total population. I will introduce you to other ratios as we go along. Of those ratios shown, I want to ask which groups are represented most. Now notice this, because I think it's important that you see it for yourself. We deal with infants, right? And mothers. Have I covered them all? Here's another one. So the majority, we have 1, we have 2, we have 3, we have 4. So of the 8 that I'm showing you, we focus on infants and mothers. Now, people say, well, how come? Well, our laws were originated from those in England. And English law favored women and children. And we thought we would see that on the Titanic, where women and children would be put into the lifeboats first, if you happen to see that movie. That wasn't quite the case. Many of the crew were on the other side of the ship and were in those lifeboats. But generally our laws still protect women and children. And so that's why we have a number of statistics around women and children. And what went on in England goes on here, and so we're interested in the health and care of women, which is paramount. We could talk about the 2 P's, which people don't seem to understand in our society, about provide and protect. And I know that workshops with men focus on providing and protecting their spouse and their children. And all ratios here, everything that you're seeing here is a crude rate. I want you to understand that it's a crude rate, and I will show you later how to make these specific rates. But these are all crude rates. Now, here's the formula for a crude death rate. Now notice in every definition I show you, you're going to see this word ratio. And you understand that it's a rate, but it's categorized. Every one of these, rate, ratio, and proportion, are categorized as a ratio. And this talks about the deaths during a specific time period. And this is usually a year. And the total population at risk, if we were looking at the U.S., it'd be about 315 million based on the population clock, and the constant is given and provided, and it's 1,000. But it is also noted in other places as 1,000 or 10,000 or 100,000, so this is 10 to the nth. Okay, but this is the standard formula for a crude death rate. Now I want you to know that oftentimes these statistics are referred to by their initials. So we got CDR, and you'll see that, and the expectation is that you would know what CDR means. Okay, making crude death rate specific. How we do that is by demographic variables. Okay, and these are a list of demographic variables. I'm trying to see whether there's any terms there that you might not be familiar with. Socioeconomic status has to do with household income. That's one way to look at it. And we don't have them all here. We could look at other factors like reading grade level or ability to understand medical information. Now, here's a table that takes a death rate, and there's about 18 formulas here, and you can see a death rate is crude, and then how you're going to make it specific is by all of these other factors. And once you do that, once you divide the population into these other factors and put it in the numerator, you are talking about a specific rate. So all of these are made specific by these factors. And you notice what the denominator is. It's the estimated mid-period population at risk. So you can go through and study these to see how every one of the others that I showed you from the U.S. Bureau of Statistics can be made specific. And here's the table continues. So you can see I'm not having you learn all of those statistics that are available by any means. There's plenty of others, and this just gives you a good introduction to them. Okay, let's go back to computing accrued death rate problems to see whether I've communicated well. Now, if we were going to look at this, CDR, right, crude death rate, and this is a heuristic illustration, so it's not necessarily a realistic one. It doesn't involve the population of the U.S. You will note the following factors. Okay, if I was going to ask you, compute the specific death rate, what would you use for this particular problem using the standard K? Okay, now you could assume, let's just assume that these are three different groups. One could be from New York, and one Chicago, and one from Los Angeles. Doesn't seem very realistic in terms of population size, does it? But the answer is going to be coming up in a future slide, but I'd like you to think about it just for a minute, and then we'll go to the answer. Okay, here we go. Now, we ask, what is the crude death rate for population A, B, and C? Okay, and what would calculating other ratios tell us? Well, it would provide hints about determinants that might explain the high high CDR among cities, or the crude death rate. Now let's focus on this. Okay, the crude death rate for population is 22. That was the total, remember? And let's go back and look at that real quickly. That was the total. That was 22 divided by 5,000. The next one is going to be 13 divided by 7,000, because that's the crude rate. And these would be specific rates because they have to deal with demographic information, in this case age. And the last crude rate would be 18 divided by 10,000. Let's see what we've done, or how well we've done with this particular example. Okay, this is what we know. Okay, our crude death rate is 4.4 per 1,000 individuals. That was in population 1. It's 1.9 deaths in population 2, and it's 1.8 deaths in population 3. So what would you conclude from here? The answer would be, from an epidemiological perspective, is that more people die in population A than they do in population 2 or population B and C. And you'll notice that there's not much variation, 1.8 versus 1.9, between population B and C, or C and B. So, and again, these descriptors generally do not follow when you're reporting data of this nature. Now, why are more people dying in population A than they are in B and C? And what statistic of the few that you've learned would you use to help answer this question? Well, let's think a minute. Is there anything that you noticed, and I didn't give you a chance, and you can go back and study the graphic yourself again, is there anything you notice about the distribution of the data that seems particularly peculiar, and how would you find that out? Okay, well, what we would do, we would look at the age groups. We'd look at the specific data, and that we might compute proportions of people between the ages of 55 and 64 for each of the three populations and see how they vary. Okay, so we see in population A that we have 4,000 plus another 1,000, and times 100%, so there's 80 people in the 55 to 64 age range. In population B, there are 28%. In population C, there are 40%. Now, population has the highest proportion of people ages 55 to 64 years of age. So we assume that the older you are, the more likely that you're going to die versus those in the other two populations in which they are younger. So we've combined and utilized two statistics in order to provide information about why we are recognizing and seeing more deaths in population A than the other two populations. So I want you to begin to think that, oh golly, only three statistics, but there's a lot to be gained and learned by the use of the combination of them. Okay. And we covered this, what they're dying from, and we think that age is one factor. It's a demographic factor that we use, and age and sex generally are the two factors that we look at most often. Okay, now let's talk about crude birth rate. And again, you see the word ratio, but we know it's a rate, and here's the formula for it. Number of live births over the total population at risk times 1,000. Okay, let's look at an example. Now, remember, tables don't always come to us in an organized fashion. Frequently, data is not organized the way we would logically think it would be. Now, if you were going to logically arrange this, what would you do? Probably you would move year to the left, and then you'd have number of live births in the population. And then you would go through the calculations following the formula, and using your attack skills, you would write down the information that would be in the numerator and that information that would be in the denominator to come up with your answer. So if I think you understand what I'm saying, and so this would be the crude birth rate for each decade, right? We are looking at 1970, 1980, 1990, and 2000. So that's the difference. So we're paying attention to those years. In a 1970, you can see what we have, and you can see how we divided it and multiplied it and came up with the answer. You can see it for 1980. You can see it for 1990. And you can see it for 2000. Now, the crude birth rate, it was much higher in 2000 than it was in 1970 and the other years that we examined. Now, you say, well, golly, why is 1980 so much lower? Why was the birth rate significantly less or far less than the other years? Well, it really had to do with the nature of the economy. We didn't have a good economy in the 80s, and so people don't consider that a baby is really a necessity, and that's something that they can put off. We even have the thinking now going on in the country that some couples don't want to be parents, and that's where we're getting down to the 1.9 children per family. They don't have any desire to parent, but normally what it has to do with the economic well-being of the country, and it wasn't good at that time. We had greater confidence, obviously, in 2000. So if you read, there's a book called Aftershock. It's been revised and updated by Bob Weidemeyer that predicts a protracted recession in the fourth quarter of 2013. Well, whether that comes about or not, I don't know. But it will 2013 will probably be a year, or 2010 data would probably reflect another reduction in birth rate. So what's the trend? Well, we have many different types of trends, and there's two trends that are very common in epidemiology. They're called a J-shaped trend and a U-shaped trend, and I'll show you those here in a minute and what they mean. So But I did want to mention that in the 80s, unemployment was significantly high, and that's one of the factors that we contribute to the fact that there was a reduction in childbirth. Okay, so this will help summarize what I've said. Okay, now I want to talk about that U-shape and J-shape curve. You can see that we just took the data from from that which we calculated in the prior slide, and we're looking at number of births from 1970 to 2000. We're looking births per 100,000. This is typically the way it's done. And so this would be your y-axis, and time would be your x-axis. Now you can see that this is really a J-shaped curve. Now to make it a U-shaped curve, we would bring it. We would have to have 25 per 1,000 in 1970. Now, as I say, these are generally the trends that we notice with various behaviors in epidemiology, and if asked to guess, what would you say about the data over time, especially with a rate that covers annual periods or decades, is that it would be either U or J-shaped. There are other trends, a linear trend, which would fit the data, probably goes something like this through the data. There's exponential and logarithmic too. So that's just to give you an idea about these trends. So I mentioned where the dependent variables are located in terms of on the last graph. It's running up the left side, and across the bottom is the independent variable, and that covers the x-axis. So if you talk about a y-axis, it's running up the left side. You're talking about x-axis, it's running across the bottom of the graph. Okay, and we talked about the various types of graphics that we have, and are the trends that we have, and ours in this case would be described more as a curvilinear trend. And let me go back and show this to you real quickly. That's not a straight line, that's a curve, so hence we call it a curvilinear trend. Oftentimes we use a best fit regression line, which is a straight line to summarize data, but the best representation here again would be a curvilinear trend. And I won't talk about time series data at this point. You've gotten enough information, and the information I want you to have at this juncture. Okay.